Hello, everyone. Good afternoon. Welcome to today's lecture. It gives me great pleasure and honor to introduce today's speaker, Professor Kazuhiro Nakadai. I will try to be brief in the introduction. Professor Nakadai received his bachelor's, his master's and PhD all from the University of Tokyo. He also has a significant amount of working experience in the industry. And currently, he is a principal scientist for Honda Research Institute, Japan. He also has a concurrent professor position at the Tokyo Institute of Technology and also other universities as well before. His research interests include AI, robotics, signal processing, and computational auditory scene analysis, robot audition, and his team has done a lot of work on robot audition and computational auditory scene analysis, etc. His work actually has received numerous awards from domestic and international organizations, and it's probably not very exaggerating to say that most of the people who do robot audition in Japan are either colleagues or academic descendants of Professor Nakadai's group. On a personal note, I got connected to Professor Nakadai through one of our previous active members, Sue. Sue did his PhD in UTS and actually did some interns in Professor Nakadai's lab before. And actually Sue's thesis is on robot audition. And in recent couple of years, I became interested in the topic. So we have had some communications recently with Professor Nakadai. So I've invited him to give this lecture. I also have a special request for him to split the talk into two parts. The first part, he will talk about his research on robot audition. In the second part, he will share his experience working concurrently in academia and also in industry, since he's also a principal research scientist for Honda Research Institute. So Professor Nakadai, please, welcome to, thank you for giving this lecture. Welcome to virtual ACFR.
Okay, so thank you very much for your introduction, Dr. Kong. So my name is Kazuhiro Nakadai. So today I'm going to talk about robot audition and computational auditory scene analysis. And maybe so you are not so familiar with robot audition. So I'd like to start what the robot audition is like. And please look at these pictures. So both robots were announced as communication robots in early 2000s. So they have a function to communicate with people, but the only people who marked as red circles can communicate with the robots. I'm not sure how many people know why, but it is obvious when you look at their mouths. Yes, they have headset microphones close to the mouth. So we feel that it is not natural and the robot should listen to sounds with its own ears. But it is not so easy for the robots. So please look at this picture. So when the robot tries to listen to this guy, so automatically, so other sound sources are mixed into the input. So in addition, the robot includes a lot of actuators that make a relatively loud noise because the noise is close to the microphones. So the robot has to deal with a mixture of sounds in a daily environment. So we proposed robot audition to solve this problem in 2000 together with Professor Okuno, Waseda University. So it is proposed as a research area to bridge the gap between robotics, AI, and signal processing. Since it was difficult, to find researchers who are actively working in all three areas, so we had a hard time finding colleagues in the beginning. But now, so we can find many colleagues all over the world. So one of the reasons why we are able to gain colleagues was our educational activities, such as organized sessions at the top international conferences like IGSVD and IROS, and hands-on tutorials of our open source software hack and some other activities. So as research topics, we defined sound source localization, sound source separation, and speech recognition as primary functions in robot audition. So for each, we have developed methods to be able to work real time in the real world. Okay. So in addition to these three primary functions, we also developed essential robot functions such as barging able function, ego noise suppression, post-filtering, and so on. So our results were published at top conferences and journals for three research areas: robotics, AI, and signal processing. So in 2014, we had very good news. The robot audition was registered as an official keyword of IEEE RAS, Robotics and Automation Society, so which took 15 years after the proposal of robot audition. So I'd like to give you a basic idea to solve the problems in robot audition. So this shows a conventional dialogue system, including a microphone, ASR, and dialogue modules. So as I mentioned, noise is mixed into the input here. The performance of these modules drops. A robot audition system typically introduces a microphone array like this, which consists of multiple microphones. It provides the primary robot audition functions like sound source localization, separation, and automatic speech recognition for separated speech. So the key idea is to introduce a microphone array. So how to use a microphone array? So this slide shows a rough sketch of microphone array processing. So using multiple microphones, a directivity filter is produced like this. So since the filter looks like a beam, so microphone array processing is sometimes called beamforming. So different from a gunshot microphone that mechanically produces a directivity, this directivity is produced with a software algorithm. So this direction, the direction of the directivity can be controlled by software parameters like this. Okay. When this direction matches the sound source direction like this, the output of the filter becomes large. So this direction is regarded as a result of sound source localization, and the output of the filter is a result of sound source separation. The main problem is how to design this beam. So we have developed our own algorithms for three primary functions. So I'd like to introduce them. Oh, so maybe I have to share the screen again because I have to share the sound also. So I forgot it. So maybe I need to do it. Okay. Can you see the screen?
Yes, we can.
Okay,
Yes.
okay, okay. Okay. Okay, the first is the sound source localization. So using a drone here with microphones for search and rescue task. So in this figure, 16 microphones were attached behind each black fur. So black fur is here. And the drone is flying here. And it tries to localize the voice uttered by this person. So we recorded this scene in advance and then analyzed the data, recorded data. And this is a reconstructed scene. The drone and person are represented as this black object and the white object, respectively. Okay, so let's watch this movie. So when the sound is localized correctly, you can see the red line like this. And the sound you are hearing is the sound recorded by this camera, but the sound recorded by the drone is actually different. So you cannot hear any speech now, but sound source localization works in this noisy environment. So you don't hear any sound, but any speech, but it can process correctly like this. So in our evaluation, it can localize sound up to minus 15 dB, which means that the power of the noise is 5 times larger than that of target sound. The next one is sound source separation. So this demonstration was recorded during 1 week visit to Willow Garage, which is very famous for loss, I think. And the room was big, like 20 meters by 10 meters with high reverberations. So let me play the mixture of sound recorded here.
Having fun. So tell me more about this robot. Tell me how you all the programming behind it.
Yeah, it's really mixed by 4 people. And then after the sound source separation, so you can hear separated sound. This is for the Toka 1.
Having fun. We went over to Rudy's Hub, and it was kind of cool because the whole idea about it was watching Dallas.
Yeah, it is not perfect, yeah. But I guess that you can feel that the sound source is well separated. So I'd like to emphasize that this was attained within a single week with little effort, thanks to hack. Then the last one is speech recognition. So this is a meal order taking task. So please watch this movie. So in Japan, we have a legendary person called Prince Shotoku who could listen to 10 petitions at the same time. And we tried to exceed his capability. And then 11 people here, they spoke at the same time. Yeah. And then robot localize each sound, separate each sound, and then recognize each speech. Then if the recognition is correctly done, so you can see the green letter correct here. So in this case, we use the 16 microphones around the top of the head here, okay? And then of course, this is a champion case. So the average success rate is something like 30% when we use a old-fashioned ASR system. So now we can use the deep learning-based, very advanced speech recognition system. In that case, probably the accuracy will improve more. Then since we developed the primary functions of robot audition, we decided to open our implementation to the public, which is called HACK. The goal of HACK is to foster collaboration between various research groups all over the world and contribute to the research communities. So we released HACK in 2008 and gives hands-on lectures every year. For example, this year we had a tutorial in ICHIKAI 2021, which is the biggest international conference in AI. The total amount of downloads reached around 200,000, but you may think it's not so many. Yeah, yes, but HACK is constantly downloaded every year. So we are proud that it has been used as a research tool for many years. So there are mainly 2 advantages in HACK, user-friendly and online and real-time processing. For user-friendly, so web-based GUI programming environment is supported like this figure. So you can use apt for installation and when you use Ubuntu or Debian-based systems, so it's easy. And rich documentation such as manual, cookbook, tutorials are also available on the web page. For online and real-time processing, so most algorithms are implemented to work online. So we can receive some FAQs. For example, what is the best microphone array? How do I get it? And so on. And so we supported actually commercial microphone arrays, but they are easily discontinued. So it's very difficult to catch up. So we developed an 8-channel microphone array called Tamago, shown here. And it is available with $300 US. So after the release of HACK, so we try to apply HACK to many domains. For example, so we made 1-minute scene ARM-based board, which HACK is running on real time. So that board was commercialized as RASP-MX in 2016. So I'd like to show you 2 applications using this board. This one, so this one, so we attached this board behind the tablet and put 8 microphones around the tablet. Okay. So the tablet can localize, separate, and recognize each speech and show the translated text to each mother tongue with the proper orientation. So now he spoke in English, and it is translated into so several languages here. Now it's Chinese, I think. Then French. Yeah. And so this is another example to introduce RASP-MX in a car. So we put 4-channel microphone array as a map ramp position, and also a small robot agent here. Okay. So thanks to HACK, the agent can understand the driver's voice. So even with loud noise, so it can control the music. Now another person spoke to the robot. So because the HACK has sound source localization function, so it can distinguish between 2 passengers. So we try to apply HACK to cloud service for discussion analysis here. First, a microphone array installed at the center of a desk here, and the discussion is recorded. Then after that, localization and separation are performed in the cloud side. So you can hear the result. So then the discussion can be analyzed based on these results. For example, speaker types such as leader, followers, and so on. Oops, sorry. So like this figure. So one of my colleagues established a spin-off company and to use this technology for educational purpose in 2017. Okay. So we are focusing more on social implementations such as search and rescue, ecology and monitoring, and hearing difficulty support. So I'd like to show you each by each. The first one is rescue and search. So in the last decades, we have experienced many disasters like these pictures. So in these pictures at a glance, you can realize that transportation systems are paralyzed and emergency vehicles cannot be dispatched. So on the other hand, faster actions are desired in these situations. It is said that survivors have to be found within 3 days, which is called golden 72 hours in Japan. So to solve such problems, so we participated in Tough Robotics Challenge. It's a big national project from 2014 to 2019. So first, we focused on drones that can solve the problems because it moves quickly and widely, even when the traffic is cut off. So as shown in the previous slide, we are developing sound source localization, which can be applicable to drones. But in the previous movie, all processes were done offline, and we could spend a lot of time to record and analyze the data. But in a disaster site, we need to do it online immediately. So to do so, we modified a drone system to make the setup faster. So actually, we reduced the setup time from 2 hours to 40 minutes. So I don't say the details, but yeah. So to operate the system even in a rainy condition, so a water-resistant microphone array has been also developed. Yeah. And this shows the live demo we had during the project. So please watch this movie. So drone is here, and the operator can see this screen. So these are synchronized. So now you can see the red person here and here. So he will utter something. Yeah. Now he uttered, and then his position is successfully detected like these blue circles. So now the drone is going to this pipe. So in the pipe, a person is here. And he also says something like, help me or something like that. IT is detected successfully here. So the sound source or survivors can be detected even in a drone noise. So we proved our robot audition technologies. It's very effective. Okay, so in addition to drone, so we had another activity for horse type robot. So this is horse type robot. This robot will be used to identify precise location of a survivor in a lab after detecting an approximate location by the drone. The operator uses a camera at the tip of the robot here to find the survivor. And when he or she is found, the operator tries to communicate with the survivor using a microphone and a speaker installed in the robot. So since the robot is driven by serial vibration, so you can see this, and then the problem is vibration noise. So you can hear the noise. So this is noise when the robot is moving. So for this, we developed noise suppression based on low-rank sparse matrix factorization. So the sound before suppression. So you can hear the voice, but it is contaminated with the noise, okay? And it is enhanced like this after the suppression, okay? So yeah, it is effective, I think. The fourth type robot had another problem on posture estimation. So when we use a conventional sensor like IMU, drift errors are summed up and the total error becomes large. Since sound source localization does not include drift errors, we integrate sound source localization and IMU and achieve 0.2 meter error when the length of the robot is 3 meters, even with this kind of obstacles. So you can see red line, that is ground truth, and the blue line is estimated posture. So you can see these are very close. Okay. So the second is application to ecology and monitoring bird songs. So in ecology, collecting bird song data is essential to behavioral studies to understand birds' pairing, male fighting, and feeding behaviors. So, but the collection is basically done by experts. Say they get up early in the morning, go to the forest, close their eyes, listen to bird songs, and write down when, where, and how information on bird songs. Of course, even experts cannot avoid human errors and tend to listen only to what they want, which results in missing important sounds. Collecting bird songs is also conducted by the government for long-term monitoring. This is essential to long assessment of the environment. For the moment, so this monitoring relies heavily on well-experienced volunteers. But due to aging, it is getting difficult to secure the required number of volunteers. So we believe that robot ocean technology can relax these problems. So this figure shows 2D or 3D sound source localization of bird songs using 4 microphone arrays marked as these red dots. And blue dots are estimated bird song locations, which coincide with locations where birds are often observed. So, and then, so right here shows the confusion matrix of bird song classification. Since this site is in the suburb, non-bird song sounds, such as cars, are also considered as sound classes. The total accuracy was over 80% when we use CNN. So overall, we verified that the robot ocean technology are effective for bird song analysis. So because each type of information is extracted individually, so it is necessary to visualize all type information to better understand the situation. And so this is one example of visualization using VR. So this is reconstructed with the information extracted only from microphone arrays. Okay. So this is actually the users see this scene in 3D. So because the label is shown as a bird position like this, so it is easy to see what birds are singing. So this black-faced banding. This is very famous bird in Japan. And you can see the crow is flying like this. This is also tracked from the bird songs. So this may be helpful for learning bird songs and increasing the number of people who can help bird monitoring. Okay. So we are also conducting scientific research on bird song analysis. So I will introduce 2 examples. The first one uses playback experiments, which we are conducting together with Professor Suzuki, Nagoya University. So we set up a loudspeaker and played back bird songs. And this experiment has been conducted for many years, but the analysis was done manually before. So we selected this time spotted towhee, so in California. So these figures show the result analyzed with robot ocean technology. So this bird has 2 types of song, that is called song and the call. Song is basically used for pairing, and the call is used for claiming a territory. So we played back 2 types of songs and found that when songs were played, the surrounding birds were singing at a higher frequency, moving more frequently closer to the loudspeaker. So this is consistent with previous findings in ecology, and it supports the idea that robot audition technology is effective for this kind of analysis. So another is the observation of owls. So owls are endangered species, and passive observations are required to avoid affecting them. And they are also nocturnal birds, so we need to observe them at night. Therefore, sound is very important cue. So Dr. Matsubayashi, Osaka University, is recording the call of the owls with a microphone array and analyzing their behaviors. In the left figure, we could identify the pathway by which chicks spread out when they leave the nest. In the right figure setting, we could track feeding behaviors. In both cases, it's easier to observe and analyze a wider area than using a night vision cameras. So this shows the effectiveness of robot audition technology. The last one is to support communication with hearing difficulties. So communication with the hearing difficulties is generally time-consuming because it takes time to write down, I mean. So accurate communication is difficult because it is hard to write down precisely. The person in charge of writing finds it difficult to actively participate in the meetings because of the burden of writings. So in Honda, so we are challenging to solve these problems using robot audition technology. So this is called Honda Communication Assistance System and the HCAS. So in this system, so mainly deep learning ASR techniques developed in robot audition have been introduced. And currently, so we are developing a new version of CAS to deploy it to all Honda departments. At the same time, we consider how to change our awareness for the hearing difficulties. So because the introduction of the system cannot solve the problems perfectly. So I'd like to touch on the future of robot audition. So we gained a few insights from our experience of the development of robot audition technology. The first, robot audition technology itself is useful. An AI speaker is a good example of a commercialized product and introduces robot audition technology. It can be said that robot audition technology have proven to be useful in the development of such a product. On the other hand, there are mainly two issues when considering practical use. One is error accumulation in module integration, and the other is the gap with easy-to-use technology. This is typical diagram of robot audition system where several modules are connected in a cascade way. Okay? So even when each module has high accuracy like 90%, the total system accuracy drops to around 70%. So to solve this problem in deep learning, so end-to-end training is in fashion. So because it provides a framework to optimize the system by minimizing the total errors. But in reality, end-to-end training sometimes doesn't work properly. So this spectrogram represents a mixture of frog call, human voice, and bell sound originating from different directions. So when we simply applied end-to-end training for an integrated task of localization, separation, and classification, so in this case, the separation doesn't work well for bell sound. So this is because the task is so complicated and the training resulted in the local optimum. So you may say that when we have more data, this can be solved. Probably yes. But it is not always possible to obtain more training data. So one of my students, Dr. Sudo, has been tackled this problem and found that performing split training before end-to-end training is effective. He also proposed a good way to decompose a task, but this has not been completely solved yet. So it is still an interesting research topic. So we'll pursue this topic further in another project. So another challenge is to make the technology easy to use. So microphone array processing requires the exact location of the microphones or transfer function between each microphone and a sound source. This information is obtained through a lot of measurements. But each time the environment changes, these time-consuming measurements should be reperformed. So this is a crucial issue in practice, and we are working on automatic calibration of the position, orientation, the offset of microphones and microphone arrays. So one of the latest results is shown in this figure. The position and the orientation of the microphone arrays appears to be well estimated, but actually accuracy is not sufficient at this moment. So we will continue with this topic. So another problem is related to the formulation of beamforming. So most algorithms assume a point source, but it is not realistic. So we need to deal with a sound source, which has a certain region. So we are developing surface sound sources extraction and spot forming to solve this problem. So this figure shows an example of spot forming. So even when there are two sound sources, and so in the same direction from a single microphone array, so from this microphone, these are in the same direction, and from this, so these are in the same direction. So in that case, spot forming can separate the two sound sources and then extract it, center this sound source well. So I presented an overview of Robot Audition, its applications, and practical issues. So Robot Audition was proposed as a multidisciplinary technology between robotics, AI, and signal processing for the purpose of improving the listening ability of robots. So we still have many challenges, but one key idea to solve them is for both academia and industry to work well together as they complement each other, so shown in this figure. So thank you very much. This is the end of my the first part of my presentation. And so can you present the second topic now, or you need to have a break?
Yes, please go ahead.
Okay. Okay, second topic is regarding the career. So actually, so I have two positions in academia and in industry. So, and the title is academia and industry. So maybe this is good for students, I think. Okay, I don't know the situation in Australia or other countries, but I'd like to talk about Japanese situation a little bit. So in Japan, so most students go on to work in companies after the graduation from the master course program. And a small number of students go on to doctoral programs. And such students basically have academic positions after the PhD degree. So this is because Japanese companies do not hire many people with PhD degrees. Yeah, they think that the people with PhD degree is too specialized. And then, yeah, I don't think it's a good idea, but in Japan, so the company tend to have such ideas. Then actually, so I took the typical strategy after the graduation of master course, and I joined NTT, which is the telephone company And then I worked there as a system engineer. After 4 years, I quit NTT and started a new research topic called robot audition. So in a national research project. So I received a PhD degree here and back to industry again in 2003. So for these around 10 years, so I could run academia and industry individually well. So, and it happened that I was offered to have a laboratory from Tokyo Tech in 2006. After that, I have 2 positions at the same time. Then I have continuously tried to maintain a balance in both academia and industry. So this is my view of academia and industry obtained from my experience. So as you can easily imagine, the goals are quite different. So education in academia and project completion in industry. And this table shows the various pros and cons. But I don't explain the details, but the important thing to remember is that these 2 parties have complementary relationship. Okay. However, if people belong to one of them, they tend to lose understanding of the other. So we should understand both very well. That is important thing. So when you'd like to understand both, I think there are 2 options. So one is that you experience academia and industry in turn. So this is a good way because you can focus on either academia or industry. However, you should be careful that job continuity will be lost by switching between the 2. It sometimes affects your promotion in the long term. So the other is that you do both simultaneously. So it looks easier to have collaboration between academia and industry, and in most cases it is true. But be careful, it is much tougher than the first option. In addition, in my experience, even when a good collaboration between academia and industry is established, technology transfer from academia to industry is still tough. So anyway, you need to draw a big sketch of your career and decide which is better. So I recommend the first option when you are young. So this is my advice when you selected the second option, unfortunately. The first, you should set up a sustainable environment, especially in the case of industrial position. As I mentioned, the company is affected by financial situation, and it is difficult to maintain the sustainable environment for a long time. The second, you need to academia-industry collaboration based on mutual concession. Yeah, because too many demands from one side will be the beginning of a collapse. I think that these 2 are minimum requirements to get a chance to overcome the valley of death or the devil's river. Finally, so I'd like to give you take-home messages. There are mainly 3 things you need to consider, I think. The horizontal integration to expand your fields. Vertical integration based on academic industry collaboration. And continuous stimulation to the society. Because people are good at forgetting you and your achievements. Okay, thank you very much. That's all.
Thanks, Professor Nakadai, for a fantastic talk. Guess we are now open to questions. Anyone have a question can raise up hand, and we'll have the Q&A time.
I've got a question. Very nice talk, thank you. I was wondering how many microphones do you actually need? So you typically have like 16 microphones or something like that, whereas we humans, we only have 2 ears and we tend to do quite well. Like, could a robot with, say, 2 or 3 microphones still get those 10 orders right, or is that just impossible?
Okay, thank you very much. I think it depends on the application. So, and if you need only the horizontal localization separation, please 8 microphones are enough. But if you need more, for example, elevation or horizontal azimuth, so that is 3D type of localization separation, in that case, the microphones should be layouted like a 3D way. So in that case, 16 microphones should be necessary. Yeah. So actually, I started the robot audition with 2 microphones, like human and animals, and then we could show some achievement with 2 microphones, but actually the performance was not so good. Yeah. Then we switched to the microphone array. Then probably 2, in terms of engineering, 2 are not enough. So maybe more than 4, the 8 might be good. 16 will be okay, I think.
Thank you.
I've got a question regarding to the applications. You mentioned a lot of application in the Japanese context. I'm wondering what other application areas that people are looking at internationally. For example, a microphone array-based robot audition systems being used in underwater robotics.
Sorry?
In underwater robotics?
In what kind of robotics?
In underwater robotics.
Underwater robotics, okay. Yeah, that is kind of a frontier field for me. So I'm always looking at such kind of presentations, and they have hydrophones and not microphones. And then, but algorithms are almost similar to microphone array processing. So we are thinking of applying the technology to underwater robotics, but not yet.
Okay. And also regarding the search and rescue application using drones, have you or your team done any experiment in real scenarios?
Yeah, that's a good question. Yeah. So actually, so when the disaster happened, yeah, actually a few days ago in Japan, we had a disaster. So yeah, but in that case, so it's very difficult to go there. So because the government stops such kind of activities, that we need a permission to do that. It's really tough. Yeah, for the moment, we cannot do that.
Okay. Let me ask another question. I noticed that you mentioned calibration of microphone arrays in your presentation. Actually, I'm personally very interested in the topic. Assume there will be some nominal parameters from the manufacturers. So what is your suggestion in using off-the-shelf products in building a system?
Yeah, that's a good question. Yeah. So as I mentioned, so we can do the calibration to some extent. But so when we consider the microphone array processing, the accuracy is not sufficient yet. So we need to improve the accuracy more when we consider the product or application. So yeah, that's why I'm working on this topic for many years. Actually, the first one is 2012, and still we are working on that. So yeah, around 10 years we already worked on that. So, but we need a more exploration, I think. So does it make sense?
Yeah, I'm just wondering, you know, in terms of the accuracy or convergence of the calibration process, I think there's a scope to develop further research.
Yeah, once it converged, maybe so it changes easily, or and then it should adapt to the change of the environment. Yeah, that is really tough.
Any other questions from the audience? If there are no questions, please join me in thanks Professor Nakadai again. And we will have a short-term discussion after the meeting. If anyone would like to join, then please.
Okay, thank you very much.
Thanks everyone.